Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called optimization of multi-level inventories mathematical modeling. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Multi-level inventory optimization. It corresponds to a mathematical model that is used to comprehensively plan the inventory levels of a distribution chain that links factories or ports, distribution centers and points of sale, determining the parameters of the inventory policy in each node of the distribution chain. Simple inventory optimization. Simple inventory models focus on the point of sale, or product use, and ignore the topology, structure, of the replenishment chain. These models can be optimization, but by ignoring the replenishment chain, they cannot be optimal, and as it is commonly said, they leave part of the money on the table. Not using mathematical models will be leaving all the money on the table. HI has developed a model for multi-level dynamic inventory optimization, multi-echelon dynamic inventory, MEIO. HI-MEIO is integrated by non-anticipative stochastic programming models, based on random scenarios, to determine the optimal inventory management policies in a multi-link, multi-level distribution chain. The objective function is to minimize the sum of the expected costs of storage, purchase, transportation, and lost demand, during a planning horizon that can cover from a few weeks to several months, considering spatial location of distribution centers, location and demand from end customers, distribution center capacity, purchase cost, working capital availability, includes financial risk control concepts. The definition of inventory management policies focuses on minimum inventories of raw materials, spare parts, in-process products and/or finished products, and quantities to be ordered throughout all the facilities of the distribution chain that participates in the attention of the end customer's orders. The Aberdeen Group states that MEIO users increase inventory turnover by 28%, and they are 2x more capable of balancing inventory and service cost effectively. Economic added value. The benefits of inventory optimization are well established by hundreds of companies, of all sizes and all economic sectors, since this is a function that occurs in all companies, both companies dedicated to the production of products and/or services, and those dedicated to the trade of products. Leading organizations have shown that right-sized storage and restructuring where and how inventory is held can yield great financial benefits and generate significant value for the entire enterprise. When mathematical models are compared to best practices, they typically reduce inventory levels by 10 to 30%, while increasing service levels. The hypotheses of academic models for inventory optimization are: the demand for the product is constant, or has a small deviation, but it is known with certainty. The delivery time is constant, or has a small deviation, but it is known for sure, and the delivery is reliable. No partial deliveries are presented. There are no restrictions on the storage area, nor on the transport capacity, which condition the quantities to be ordered from the supplier. The demand for one product is not interdependent with the demand for others. There is no correlation, therefore, decisions in this regard can be made without considering multiple products, and the only two costs involved in the operation are the cost of handling the product and the cost of managing it with the supplier. Unfortunately, the assumptions of academic models are not fulfilled in real industrial cases.
Policy S. When inventory is at or below the reorder level, S minuscule, a purchase order is generated to reach the inventory level, in hand plus in order, S capital. Policy, S, Q, when inventory is at or below the reorder level, S, a Q size order is generated.
Stock-based policy, S, the inventory level must be kept as close as possible to an S inventory level. Demand modeling. For the evaluation of the cost of decisions, the real demand is taken as a reference, coming from history, which is variable over time. The modeler's position is to decide which form of variation to assume for demand, considering the availability of degrees of freedom, which he has with respect to the calculation of the parameters of the mathematical model. There are at least two modeling possibilities. Static, its probability distribution function does not vary over time, and dynamic, otherwise. With respect to inventory policy, this can be static, its quantitative parameters do not change over time, and dynamic, otherwise. The table presents the rational possibilities, ordered by their complexity. Replenishment process, lead time. Delivery time corresponds to the time it takes to complete a specific process. In business, lead time defines the time it takes to process an order, manufacture a product, deliver a good, or a combination of these processes. In inventory management, lead time is important as safety inventory levels are proportional to this variable, which is indirectly a consequence of the decisions made. The delivery time depends on the replenishment chain. It can go from suppliers to factories, and from there to points of sale, passing through distribution centers. The total delivery time will be the sum of the production time plus the distribution time. Mathematically, it will be true that the total expected delivery time will be equal to the distribution time plus the product of the probability of shortage of the raw material, multiplied by the production time. This value will be related to the probability of shortages of the final product. When a multi-level chain must be managed, decisions must be made simultaneously for all inventories and all links in the chain. Policies must be defined for factories, which require inventories of raw materials for production, and policies for inventories of final products that must be supplied to distribution centers. In the same way, a coordinated, optimized policy must be defined for the relationship between distribution centers and points of sale. This relates the levels of safety stock, SS, that are required, according to the level of service alpha wants to provide. Policy inventory safety stock, SS. To calculate the safety inventory, the first thing to do is to define the level of service that will be offered in each facility. For example, a 90% service level for a certain item ensures that with a probability of 0.90 its demand will not be greater than the supply during the delivery time, and that the probability of inventory running out will be only 0.10, 1 to 0.90. The calculation of the safety inventory is done by determining the minimum amount of material required in stock, to guarantee the level of safety. The safety stock equation is: the calculation of the safety inventory is done by determining the minimum amount of material required in stock, to guarantee the level of safety. As the equation presents, the safety stock formula is a function of average demand, standard deviation of demand, average provisioning time, and standard deviation of provisioning time. If you want to serve endpoint of sale, POS, from a distribution center, you must consider that each POS has its own SSI safety stock. One solution is to keep the SSI at every point of sale and not have safety inventory in the distribution center, SSCD. In this way, the attention to demand is independent of the delivery time from the distribution center to the POS. If you want to serve endpoint of sale, POS, from a distribution center, you must consider that each POS has its own SSI safety stock. One solution is to keep the SSI at every point of sale and not have safety inventory in the distribution center, SSCD. In this way, the attention to demand is independent of the delivery time from the distribution center to the POS. If the distribution center's lead time is 0, you could have all the safety inventory in the distribution center. The SSCD level must be defined. A trivial and non-optimal solution is to define SSCD as the sum of the security stocks of all clients, which corresponds to the upper limit of SSCD. A solution that improves the previous one is to assume that the demand for POS is not correlated. This is an intermediate solution but not an exact one, since ignoring the correlation can lead to overestimations for negative correlations, and underestimations for positive correlations. An example of positive correlation are sets of POS that sell products whose demand is strongly determined by the weather. Peaks and troughs of demand will occur simultaneously, requiring greater safety stock. The right solution is to consider the set of POSes that can be linked together and determine the optimal solution using a mathematical optimization model. Multi-level stochastic inventory optimization. The problem of inventory optimization involves uncertainty, since the reason for safety inventories is to cover the risk of shortages. An optimization problem is called stochastic programming, SP, when the problem that derives from the inherent uncertainty of the variables and/or parameters involved in the model must be faced. In non-anticipative stochastic optimization, at the beginning of each period a decision is made deterministically, and it is probabilistically known what may happen in future stages, because of the decisions of the here and now. Examples of random parameters, in the inventory problem: demand, costs, delivery time, and freight. The fundamental hypothesis is, we don't know what will happen, but we do know what can happen. The analytical landscape and the economic value added by applied mathematics. At the beginning of the last decade, IBM published a diagram, improved on the one presented by Davenport and Harris, that describes the benefits provided by analytical methodologies. As a superior methodology, stochastic optimization is classified, which can manage the effects of uncertainty in the decision-making process. Thus, ruling out stochastic simulation. The capacity of the methodologies is looked at from 2 points of view: degree of complexity, and competitive advantage. It is clearly visualized that the contribution of the methodologies is differential, not all of them contribute the same. This implies that knowledge generates competitive advantage, due to its greater ability to handle complex situations. With respect to descriptive analytics, it can only be said that its contribution is minimal, and that in practice it is not analytical. The stochastic optimization used by Mayo is based on 2 stages. First stage, related to the decisions to be made, i.e., the parameters of the inventory policy, and second stage, future simulation of on-demand service, inventory profiles, and product purchase and delivery transactions. The scenarios correspond to the random exogenous parameters that affect the company, and the decisions to the selected inventory policy and its quantitative parameters. This is for every facility, every product, and every period of the planning horizon. The probabilistic characterization of the stochastic process begins with the identification of the mathematical models of the stochastic processes of all exogenous parameters. This starts with the historical database and is specified in multivariate probability functions. Years ago, historical databases were static and changed with weeks or months. Today, databases are updated online, leading to fundamental changes in data processing. The next step is the synthetic generation of scenarios for exogenous parameters, using a mathematical model of probabilistic simulation. These processes must be carried out based on predictive artificial intelligence. The last stage is the connection of synthetic scenarios to the prescriptive model of artificial intelligence, or optimization. The result is the selection of the inventory policy to be used and its probabilistic characterization. This characterization is the empirical distribution function provided by a stochastic optimization model, defined by the following statistics in dollars. Expected value 4,597,841. Standard deviation 441,668. Maximum 5,682,184, and minimum 3,281,037. And coefficient of variation 10%. The above empirical distribution function can be replaced by a theoretical continuous probability distribution function. As the scenarios increase, the empirical function will adjust to the theoretical distribution function. Stochastic optimization corresponds to one of the methodologies of prescriptive artificial intelligence. Financial risk management. The management of financial risks is the greatest added value for stochastic optimization, since in many cases optimizing the expected value of decisions is not the right thing to do, since it can lead to risk-prone positions with high vulnerability. Consider an example where the goal is to maximize profits without considering financial risk. As a result, we have the probability distribution function of costs. After analyzing the situation, the decision maker considers that he should not assume costs greater than 3 million. To this end, it includes a downside risk restriction in the model, which limits the maximum total cost to 3 million. This will produce a new empirical distribution of probability. Risk management reduces expected cost and cost volatility, leading to greater financial stability. On the other hand, profits and service levels are reduced. This increase in cost can be considered as a risk premium. The end result of the process, which may involve multiple executions of the optimization model, will be the function of distributing the minimum cost while respecting the financial risk management policy. Expected cost versus expected cost service level. In inventory theory, the level of service can be represented by the probability of not reaching a situation of stock out. Intuitively, the service level represents a trade-off between the cost of inventory management and the cost of out-of-stocks, leading to lost sales, lost opportunities, loss of business image, and customer frustration, among other things. It is a decision variable, since it is known that the higher the level of service, the higher the cost in inventory management. From an economic point of view, it should be a decision derived from the profitability provided by the sale of a product minus the cost derived from not meeting demand. The problem with the cost of loss is that in many cases it is subjective. The Pareto expected cost versus service level curve is a means of rationalizing decisions that move in contradictory directions. If you want a high level of service, you must be willing to pay high costs. If you want a low cost, you must be willing to offer lower levels of service. When including lead time as a variable in mathematical models, it may be necessary to include constraints in the model so that certain conditions are met, for example, that they do not exceed a set maximum time. It also allows you to determine inventory policies that aim to minimize lead time, which should maximize the level of service possible. Typically, organizations must share resources in the decisions they make, as these are limited. In the case of inventories, the most important resources are working capital, labor, storage capacities, product receiving and shipping capabilities. All of them can be taken to mathematical models. This leads to more complex, but more realistic models. The current power of computing allows the problem to be solved in reasonable times. To determine the costs and profits of the inventory management policy, all important expenses and revenues must be considered. The most important are the costs of storage, unmet demand, transportation, and purchases. Distribution, replenishment planning. Inventory rebalancing. High DRP is a module specially designed to optimize the distribution and replenishment process. The general problem to be solved is, when and how much to order? How to distribute inventories in the distribution center and in the warehouses, POS. This to minimize operating costs and maximize organizational profit. For a short-term replanning horizon, high DRP takes the following data as inputs. Product inventories in all warehouses and in the distribution center. Inventory policy in all warehouses and in the distribution center. Inventory to be delivered to the distribution center at short notice, expected demand in warehouses for products to be balanced, and preset distribution routes. Optimization of the replenishment process, real case in pharmaceutical industry at Pharma Express. Pharma Express, one of the largest Latin American pharmaceutical laboratories, implemented a set of large-scale optimization models to integrate production planning and scheduling in its plants to model the process known as sales and operations planning, scheduling, production, which involves minimizing and configuring times and format changes on machines, characterize the demand for the final products, optimize inventory policies, and optimize the procurement of raw materials, and optimize the operations in the distribution chain. The diagram presents the connectivity of the models that are part of the artificial hypothalamus of Pharma Express. The diagram presents the process flow followed to meet the demand in Pharma Express. This process has three parts. Attention to demand, in green, inventory management, in blue, and purchase management in red. Probabilistic characterization of demand.
As an example of probabilistic characterization of demand, in each period, for each product, the ARIMA model, P, Q, is used, which has a deterministic component, explained demand, and a stochastic component, an error not explained by the model.
The demand for the dicetyl product is taken as a reference. It is evident that the demand for dicetyl has seasonalities and that its demand is far from constant. Similarly, its volatility is not constant and varies throughout the months of the year. The important parameters for the characterization of demand depend on the distribution functions that are going to be assumed for synthetic generation. In the case of a triangular distribution, minimum, median and maximum are required. The example presents the setting for normal distribution functions. It should be noted that the demand study is no less important than the optimization modeling. The results obtained depend on the hypotheses that are made for the random parameters. This process corresponds to the first stage, the characterization of the demand. The graph presents the synthetic generation performed with a truncated normal probability distribution. This step completes the demand modeling process. Then, the data processing is ready to begin the stochastic optimization process. Keeping in mind that the distribution of the total annual cost is a function of the inventory policy, the next step is to select the inventory policy, which can be common to all products, or individualized for each product. The chart presents the histograms of 3 inventory policies. It is evident that the SS policy produces the best results for all statisticians, including customer service. With respect to the stock-based policy, the avoided cost is 8.31%. The model then selects the SS policy for all products. This would be the first result obtained with the INV model. The model is optimized as a stochastic optimization model, in which management of risk is not optimized and only expected value is considered. As mentioned earlier, this is a risk-prone position, and it can produce the rational solution with the highest risk. When risk management is included, the problem is complicated as there are 2 decision variables that move in opposite directions. The best expected value is associated with higher risk. One measure of risk is volatility, such as standard deviation or variance. The problem becomes a 2-criteria problem, in which the decision maker is critical, as he must make a subjective decision, his risk-averse or risk-prone position. There is no single formulation on how to handle the problem. The oldest could be the Markovits mean variance problem, and the current one represented by the research of Rockefeller and Urayev. In the case of mean variance, the model uses a subjective parameter that sets the weights for each factor, expected value and standard deviation. This parameter takes values between 0 and 1, giving weight to the expected value according to the first value. The parameter is a linear convex combination of expected value and volatility. As it is subjective, the decision maker can choose any value according to his or her interpretation of the end user's risk position. The parameter should be a linear convex combination of expected value and volatility. As it is subjective, the decision maker can choose any value according to his or her interpretation of the end user's risk position. In this case, regardless of the value of the subjective parameter, the solution is always the same, the SS policy, but this is not a general rule. What is known is that the objective function is a function of the parameter in convex. The next step is the evaluation of the information provided by the demand model. The evaluation involves performing 3 runs of the optimization model, making combinations of demand modeling and inventory policies. In this case, the best solution is obtained when the demand model is closer to reality, dynamic demand and the decision possibilities are more flexible, inventory policy with dynamic parameters. Up to this stage, the INV model has indicated what type of mathematical modeling should be used. If desired, these optimization runs can be carried out with part of the supply chain, to speed up the analysis process. Using the best modeling alternative, the next step is to select the parameters of the optimal policy, for all products, all installations, and all periods. In this way, the process could be completed, without performing the financial risk analysis. The Pharma Express supply chain in the Caracas metropolitan area is composed by 1 production plant and 3 distribution centers in Caracas, Petare, and El Hatillo. At the national level, Pharma Express has 2 additional distribution centers, Coro and Acarigua. The optimization analysis of inventory policies was carried out for a reference case, in which 2 products are presented, Vuscobras and Distel. The graph presents the distribution function of aggregate demand, for 5 years of historical sample. The diagram presents the flow of products along the distribution chain. Not all flows are allowed. Each distribution center has its own aggregate demand, resulting from grouping all the POS it serves. The model must establish dynamic inventory policies in all distribution centers, for all products, for all periods. The image presents the inventory policies for 4 products on the production plant. The graph presents the results for 3 aggregate variables of the system: inventory at the end of the planning period, blue, unattended demand, red, and replacement, green. The aggregate service level for satisfied demand, as determined by the model, was 91%. The graph presents the results of the relationship between the level of service and the annual cost of inventory management. In this case, 5 runs of the optimization model were performed. Empirical curves can be adjusted by nonlinear functions. This information could be used in aggregate models, to model total cost as a function of service level, or vice versa. Multi-level inventory optimization. Computational implementation. OpTeX, Optimization Expert System, is HI's artificial intelligence that produces artificial, predictive and prescriptive intelligences. It is the platform used by HI to develop the multi-level inventory optimization model. The models implemented in OpTeX can use multiple technologies, due to the clear division between mathematical model and optimization technology. Regardless of the programming languages, the models connect directly to the IDS database, by means of SQL statements. The screenshot shows SQL connectivity to the Industrial Information System, in a GAMS program. Because the IDS data model is open, the end user can connect it to any other application developed by a third party, this for any input-output data. The fundamental elements of the OpTeX architecture are a relational information system, which integrates 2 specialized information systems. Mathematical Modeling Information System, MMIS, stores the entire mathematical modeling environment, and Industrial Data Information System, IDIS, stores customer data. The next element is OpTeX, the generative artificial intelligence in charge of interpreting the existing information in the MES, and from there generating all the computer elements that are required for the user to interact with the DSS. Based on Open Database Connectivity, ODBC, OpTeX generates the following elements: visual interface for the user to access the IDS to maintain and consult it. Interface for mathematical models to connect with the IDS, generated following the syntax of each optimization technology. This interface is part of the computer programs of the algorithms. Below are several examples of this type of component, based on SQL statements. The screen presents the menu to access the INV model databases. These are normalized according to a relational data model and can be stored in any SQL database. The screenshot presents the stock management table. The shell window presents 4 data tables that are related to each other. Final products, storages, final products, statistical models, and final products, historical sales. The shell window contains data windows, that include the warehouse's master table, from which you can access the table that describes the connectivity between warehouses, and the table of the products that can be stored in the warehouses. A dialog box is included that allows access to any table related to the seller master. The window contains part of the GAMS program constraints of a model of the Mayo system. The results are presented in browsers oriented to mathematical models. They are organized by the different elements of the mathematical model. The example presents variables, VV tables, and constraints, RR tables. From the browser, You can view all the tables associated with the mathematical models. The example presents the available inventories of the products. Inventory optimization, case study at Procter & Gamble. This case is supported in the paper. Inventory optimization at Procter & Gamble, achieving real benefits through user adoption of inventory tools. This article is the publication made to announce that Procter & Gamble had won the Franz Edelman Prize in 2010. Procter & Gamble, PANG, founded in 1837, is a leading global consumer products company with $76.7 billion in sales in 180 countries. 4 billion times a day, PANG touches the lives of people around the world through its familiar brand names, like Tide, Crest, Gillette, Pantene, and more than 200 others. It competes in 26 distinct product category markets such as hair care, paper towels, cosmetics, skin care, oral care, blades and razors, diapers, and fabric care. Over the past 10 years, Procter & Gamble has leveraged its cross-functional organizational structure with operations research to reduce its inventory investment. Savings were achieved in a two-step process. First, spreadsheet-based inventory models locally optimized each stage in the supply chain. Because these were the first inventory tools installed, they achieved significant savings and established PANG's scientific inventory practices. Second, PANG's more complex supply chains implemented multi-level inventory optimization software to minimize inventory costs across the end-to-end supply chain. In 2009, a tightly coordinated planner-led effort, supported by these tools, drove $1.5 billion in cash savings. Although case studies show the mathematics employed, of equal importance is the presentation of the planning process that facilitates inventory management and the decision tree that matches a business to the optimal inventory tool depending on the requirements of the business. Today, more than 90% of PANG's business units, about $70 billion in revenues, use either single-stage, 70%, or multi-echelon, 30%, inventory management tools. Plans are underway to increase the use of multi-echelon tools to manage 65% of PANG's supply chains in the next 3 years. Inventory optimization, a low-cost fortune. Between 2000 and 2010, Procter & Gamble, PANG, has leveraged operations research to reduce its investment in inventory. For more complex supply chains, multi-tier inventory optimization software was implemented to minimize inventory costs across the end-to-end supply chain. In 2009, operations research generated $1.5 trillion in savings. In 2011, more than 90% of PANG's business units, about $70 billion in revenue, use inventory management tools, 70% single-stage, 30% multi-tiered, and plans were underway to increase the use of multi-level tools to manage 65% of PANG's supply chains over the next 3 years. The Guaranteed Service (GS) model of inventory placement forms the basis of the multi-level inventory optimization (MEIO) tool. In the GS framework, the supply chain is defined as a network with a set of N nodes and a set of A arcs. Each node corresponds to a stage of the supply chain. A stage is a processing activity for a given SKU and location in the supply chain, such as manufacturing an item, transporting an item from one location to another, or packing an item. The arcs denote the relationship of precedence between the stages. To put this in a system context, the stages correspond to raw materials, ROH, semi-finished products, HALB, and finished products, FERT. The arcs correspond to the bill of materials, BOM, paths that convert row to FERT. In its simplest form, the GS model requires very little data. By implementing single-stage inventory models in the fabric and home care business in Western Europe, total inventory decreased by 36%. Service increased by more than 98.5%. North America cosmetics total inventory decreased by 9% during the multi-tier implementation process, which was credited with 78% of this reduction. With technology established as the backbone of optimization, sustained reductions of 2 to 3% per year have been achieved, while maintaining the level of customer service. Multi-level inventory optimization reduced the cost of safety stock by more than 17%, which equates to a 5% reduction in the total cost of inventory. This in exchange for an increase in the safety stock of semi-finished products. The image presents the partial algebraic formulation of the PANG inventory optimization model. Without fear of being wrong, it can be said that Procter & Gamble's mathematical optimization models are their golden goose. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.